Hi, it's Moser with a quick tutorial on electron affinity and electronegativity and the trends in both of those things. So after you've watched this video, you should be able to describe electron affinity, explain periodic trends in electron affinity, distinguish between positive and negative EA elements, as well as being able to define electronegativity and use the periodic trends in electronegativity to predict patterns in EN. You should already know about the periodic trends in atomic radius and ionization energy, as well as the difference between anions and cations. Okay, let's go. So I've got a drawing of our second period running from lithium to neon, and recently we've talked about the process of making an ion by removing an electron, which gives us a cation. Cats are positive. I have positive feelings about cats. Purr. And we've talked about the trends in ionization energy, but you should be aware that there's more than one way to make an ion. You can make an anion by adding an electron to a neutral atom. So when we add an electron and create an ion, we also have an energy change. You already, based on what you know, can probably guess that some of these atoms would not be real receptive to adding an electron. Well, let's explore the energy change seen in the creation of an anion and what it means in terms of periodic trends. When we add an electron to a neutral atom, we get a negative ion, and we call that energy change electron affinity. It seems kind of odd, but an atom's electron affinity is basically the difference in energy between that neutral atom and the atom with an added electron. If energy is released when the atom accepts an electron, we consider that atom to have a negative electron affinity. If energy is absorbed, that's a different problem. That means you're forcing the atom to take an electron. The electron affinity is a positive number, and that's not stable. Let's look a little bit more closely at why that is. If we look at a chart that shows a neutral fluorine atom with its little positive nucleus and 7 valence electrons on the second energy level, that's pretty high energy. And things that are high energy are actually unstable. Think about a little kid spinning wildly in the yard as fast as they can. They're going to fall down, they're going to go out of control. It's just not a stable situation. Fluorine is much more stable and lower energy when it gains an electron and becomes a fluorine 1 negative ion. So the difference in the energy of the unstable neutral fluorine and the fluorine 1 minus, where does that go? The difference in energy between the neutral fluorine and the fluoride ion, the fluorine with an extra electron, is given off into the environment. Some other atom will absorb it, don't worry about that. But because it's lower energy with the added electron, it's very stable. A good metaphor to use is that of a kid on a sled. Yes, that's supposed to be a sled, I know, it's terrible. It's the world's worst drawn saucer sled. The kid sitting up on the hill on the sled isn't stable. It's going to take something to hold them in place. They've got a lot of potential gravitational energy. That's not a terrible metaphor. Now, what happens if the kid goes down the hill? Whee! When they get down to the bottom, they don't have any gravitational potential energy. They're much more stable. They're lower energy. That's what we're talking about. When an atom, especially something in the halogens, group 17, that only needs to gain 1 electron to have a noble gas configuration, is lacking that electron, it's unstable. It's high energy. Gaining the electron lowers its energy and makes it more stable. The energy is given off, like I said, out into the environment. Some other atom will pick it up, which means that we consider its EA to be a negative number. It's negative because the starting energy of that atom is higher than the ending energy. To just make up numbers, if this is 100 joules and this is 10 joules, The difference is negative 90 joules. Believe me, these aren't even close to the real numbers. Well, what if we have an element like sodium? Sodium, with its one valence electron, would have a noble gas configuration if it could get rid of that, but what if we were to force sodium to actually take an extra electron, forming a sodium 1 minus ion? Ooh, well, energy would be required to hold that electron in place. So this is not a stable arrangement. It's totally unstable. The minute you stop holding that extra electron in place, it's going to immediately lose it and drop back to its older, more stable configuration as a sodium ion. As a matter of fact, sodium would really like to give up an electron to be even more stable. So this is what we consider a positive EA element, because the energy of that atom, once it's taken an extra electron, is actually higher than the neutral atom. So we've had to add, again, if this is 50 joules, then this is 100. The difference is positive 50. To use the kid on the sled metaphor, to use the example of sodium, we've got that kid on a sled and they're kind of halfway up the hill. They could be lower energy, but if instead of letting them go down the hill, in other words, losing that valence electron, you push them up the hill, there's no way they're going to stay there. The minute you let go of them, they're going to slide right back down to their older, more stable position, if not all the way to the bottom of the hill by giving up an electron. Holding things on hills, it just doesn't work. Now, since we're talking about periodic trends, we should talk about periodic trends in electron affinity. The halogens, you already knew this, the halogens do a great job of gaining electrons. They're pros at it. So they have a high reactivity, and they also have a very negative electron affinity. In other words, they're much more stable with an added electron. EA tends to become more negative as we go across the period. And obviously, things in groups 1 and 2 have flat out positive EAs. There's no way they're going to take an electron. What you should also be aware of is that for the same reasons that atomic radius tends to increase as we go down a group, and ionization energy over here tends to decrease as we go down a group, the bigger the atom is, the less attractive it is to those electrons. So iodine, being larger, having more energy levels between the nuclear pole and those outer shells, has a harder time adding an electron. Oh, it'll do it, but it's not as easy as bromine. And likewise, chlorine has an even easier time than bromine adding an electron. The most electronegative element of them all, why, it's fluorine, right here. Fluorine is it's got the most negative electron affinity of any of the elements in group 17. So now, oops, and I screwed up, let's go ahead and talk about electronegativity. The funny thing is, we've been talking about atoms a lot, but we haven't really talked about what they look when they're bonded to one another. So here we've got a very bad drawing of a compound that contains one oxygen atom and two hydrogen atoms. You're pretty familiar with this compound. It's water. And in fact, in any bonded compound, what we have are the small positive nuclei surrounded by that big cotton candy fuzz of the electron cloud, which is what we get, that big fuzziness, when we put all those shells together. So they share this cloud. It's kind of like sharing the blankets with your best friend while you're watching a movie on the couch. What we know is that not everybody shares equally. An electron affinity is a measure of how tightly one atom in a compound can hold on to the electron cloud. It's really a measure of the unevenness of the electron concentration. It's a measure of who's the blanket hog, metaphorically speaking. Electron electronegativity tends to increase across periods and tends to either decrease down a group or remain the same. So again, as we go this way, elements tend to become more electronegative. That seems to go with that whole electron affinity thing. More willing to take electrons, more attractive to electrons. Yeah, there's a relationship there. Electronegativity also tends to decrease as we go down a group. So, as I said, those bigger elements down towards the bottom, they have more layers of electron shielding between the nuclear pole and those outer shells. What does this mean in terms of an actual compound? Well, what it means is that when we look at hydrogen as it's bonded to oxygen, because oxygen is so much more electronegative, the hydrogens kind of get a lot of that electron cloud pulled off them. And oxygen tends to kind of hog it. I said that oxygen's pretty electronegative, but let's think through those trends. We said that electronegativity tends to increase as we go this way. Well, we don't even have electronegativity ratings for the noble gases because they don't form compounds, and electronegativity is only really measured in compounds. Which group do you think would be the most electronegative? Well, I'm hoping that you said group 17, the halogens. And since we said that electronegativity tends to increase as we go up a group, and we ignore hydrogen, which halogen do you think has the highest electronegativity? Well, I think you probably said fluorine. And fluorine, as a matter of fact, is the most electronegative element there is. We actually index other things off of that. That'll become really important in the next chapter when we start to talk about bonding and the differences in electronegativity between elements. So now's a good time to mention that all of the trends that we've talked about, from atomic radius to ionization energy, electron affinity, and electronegativity, we usually are talking about those trends within the main group. And the main group, you'll remember, is the S block and the P block. The D block and the F block, well, they're a little different. In the D block, the properties vary a whole lot less and with a whole lot less regularity than the main group. Really, the D block is just sort of more uniform. And in the F block, well, they're sort of a separate set of beasties. What you should know is that electrons are removed in reverse order, as given by orbital notation. The last in is the first to go. And they're removed from the highest energy orbitals first. Since we don't talk a whole lot about compounds made with the F block, it's not nearly as important. And with the D block, it's enough to know that their properties are fairly uniform. All right. Do you know what electron affinity is? Can you explain how it changes across the periodic table? Do you know the difference between a negative and a positive electron affinity element? And can you define electronegativity and use the trends that we see in it to predict the patterns of electronegativity? Well, I hope so. Take your quiz.